Yeah? All right. So when this flag is set, then you could enable an interrupt service routine again, like your interrupt control logic will see that this flag is set, and will then call the interrupt service routine associated with all of this, and it will allow you to understand that some new value has been captured in your registers. So that's what we're going to do. So let's first explain again what all these control registers are about. So it's pretty much the same as what we have seen before. So look at the data sheet. Position 7 and 6 are about the compare and match for channel A, 5 and 4 for channel B. WGN 11, 10, 13 and 12 is about waveforms. There's actually 4 positions, not 3 positions, that you have for timer 0 and timer 2. And it depends, and that means that you can do more complex things later on if you do pulse width modulation and so forth that we'll be talking about in the future. The pre-scaler positions, again as before. ICE S1, which is the 6th position, sets the input capture edge select to either a rising or a falling edge, meaning that if you see a rising edge on the previous slide over here, it rises, then you will do the write into the interrupt capture register. ICNC1 is the 7th position, sets the input capture noise canceller. So if you set it, you will actually do 2 measurements in a row, making sure that an actual transition did occur from say high to low or low to high. Then there's this mask register, and again we have similar positions where we can enable different interrupts. One is the timer overflow interrupt, and the others are again the compare and match interrupts that you may want to enable. Then there's another position which is the ICIE1, which is the 5th position, and that will do an interrupt capture interrupt enable, meaning that whenever, so let's go back to the previous slide, whenever this flag is set, it means that indeed something got captured right over here, the value, the counter value over here was captured in here. So when that interrupt service routine is now called, because this flag was set to high, then you can immediately start reading out this register, and you know new information is available. So you definitely want to set that if you want to work with the interrupt capture functionality. Alright, so now let's have a look. So we're going to look at the analog comparator output. So how do we generate it? So here we see AZ0, so let's go back to the previous slide. We like to generate AZ0 over here. So we're going to set ACIC in such a way that this is being forwarded, and that will drive the writes over here. So the idea is that we want our timer 2 block waveform to be pushed forward. So how do we do this? Well, first, if you look at this diagram, you see a comparison that's over here, and we will compare against something, and we choose according to this particular position in the particular register, I think it's the ACSR again, which we will use either some pin, AI and 0, if you will be able to look at the datasheet again, is some kind of input pin, that you can set it as an input pin, you can read it, or some kind of bandgap reference, which is what we are going to use, and that is being compared against an input coming from PD7, which is also the name for AIN1. So we're going to use this to compare, and we're going to connect the timer 2 square waveform, which is PB3, to PD7. So in that assignment that you will be doing next time, you will actually use a wire to connect pin PB3 to PD7. And the output generated by the timer 2 square waveform is being pushed through over the wire as an input to PD7, which is compared to this bandgap reference, and with that you'll be able to figure out to generate the AC0, and you get a falling and a rising edge that then translates into the actual routes to the interrupt register. So in combination with ICES1, which we will set to 1, we will capture at a rising edge. That's what we're going to do. And since PB3 is actually creating a waveform on a cycle-by-cycle basis, we are also going to use a prescaler for our timer 1 set to 1. So it's at full speed. That's what we're going to do. So here's a table for the analog comparator pin. So let's have a quick look at that data sheet and see what it says. And effectively over here you see all these pin assignments as well. So it's good to look at that as well. And you notice here that we have the AIN1 to be PD7. So that's how we figured that one out. Alright, so we have to talk about the ICSR. So the ICSR has a couple of specific positions that we want to talk about. And I'll be explaining the others too, but so let's do that. So the position 0 and 1 over here, those two, are about an interrupt on a toggle rise or fall. We're not really talking about it here. Positions 2 and 3 over here are about the capture and the comparator interrupt enable. So have a look at the names. ICIE is about interrupt enable, IE. That's how you can often recognize that. So then you need to write the corresponding interrupt service routine. And the ICIC is the particular bit that you want to set if you go back to this particular slide, that is going to set the mux in such a way that this one is forwarded. That's what we want to do. So let's go forward again. And position 4 is the comparator interrupt flag. So where is that? It's over here. So this is set when an interrupt happens, and it clears when the corresponding ISR executes, right? And the flag is cleared, then the ISR executes, and then it executes all its code, and then you have the final return instruction embedded at the end of the ISR, and you go back to your main code where your next instructions push forward. Position 5, where is that? It's over here, AC0, and actually this records the output directly. That's kind of interesting. So what you see here, even though that drives this particular machinery for when to capture this particular timer, it's also stored directly into that particular bit as a digital representation, as a binary representation. So you can read it, it's only readable by the way, you can see that. And the AC0, if you read it, will tell you what kind of value you have there. Is it high or low, depending on the bit value, 1 or 0. So we're going to use that also. Now, position 6 over here connects the positive input to a band gap reference if you set it to 1. And this is a temperature independent voltage reference circuitry. And usually we really do not use this because you usually have something more complex that you will build. Not something as simple as what we're doing right now. But we will be using this particular band gap reference. So that's why we are going to set it to 1 over here. And finally position 7, when this is switched to 1, then the analog comparator is turned off. So we actually want it on, so it's on the default value 0, so we want it on. So this is your ACSR register. Okay, so let's have a look at timer 1. So let's set a few of those. The first thing that we do is, so this is yet another way of showing you how you can manipulate registers. We do a 1 left shifted over ICES1 positions. That makes the bit corresponding to ICES1 1 in this particular register. And I can also just add as an integer 1, which means that the very first, the 0th position, the 0th bit, the least significant bit, will be set to 1. That gives you a prescaler of 1. So at full speed. Now, why do we do the ICES1? Why do we want to set that to 1? So let's go back again and have a look what that meant again. So we'll go back over here. It actually means that we're going to set it for a rising edge. So when you see a rising edge, then the interrupt should happen. So let's go into forwarding this code. The ICIE one is set, meaning in this mask register, meaning that the interrupt corresponding to that interrupt on capture is enabled. So when interrupt on capture happens, creates a hardware event, sets that interrupt capture flag that's being catched by your interrupt control logic, and that will then stop everything really, right, and starts executing that corresponding ISR after having saved the state, putting the program counter on the stack, and so on. Now, this particular statement over here talks about that we want to compare against the bandcap reference, and the ACIC, let's have a look again because I forgot it again, that's this particular guy over here, is about it's about this mux that we actually want this particular AC0 to be forwarded to drive your capturing. So that's what we said. Now we also need to make sure that your D7, which is equal to this particular input, which is, let's go back again to this slide, is the input over here, that pin actually is designated as an input. So that's what is done over here. Here we just create, here I just put 0 for the whole register. That's probably not the right way to program this because you don't know what you use all these other pins for, so better is to just make sure that that particular 7th position in this register is being cleared to 0 by using a proper AND operation. Now this is a proper way to set up the timer. So now what do we got? So I have a whole bunch of timers and you're going to connect those. So first, timer 0 implements your software counter, the 1 millisecond software counter. Timer 2 generates a square waveform with a period of 200 cycles. This waveform is going to drive your AC0, and the rising edges in AC0 causes the capture interrupts for timer 1. Now both timers, 2 and 1, run at full speed and they're synchronized, right? So here we have timer 1, which is this particular interrupt service routine is called when you actually see such a rising edge causing, a capture interrupt. That's a hardware event that then now calls this ISR. So what's happening over here? Well, what I would like to know is, if I generate a waveform of a period of 200 cycles, can I really measure that as being that particular waveform? So how accurate is everything? Well, let's have a T1 capture that I set to this ICR1, meaning that I'm looking at what that register has. So 16 bits, I read it into this particular guy. And I have already stored, say, a last one, and I look at the last capture and subtract this from what I just found, the T1 capture, and I get a period. Now, of course, for the next time that this is being called, I know that the currently measured T1 capture will become the last one, so that's why I have this statement. So when I go through this, I know that this period, a global variable that I will have in my program, will effectively measure the period according to how that interrupt capture register sees it. So if you have this block diagram, is it really true that I see a period of 200 or not? If you're looking at this particular guy, then this is again our timer 0, which is our 1 millisecond software timer, right? So now we have the full picture. So the idea is to do the following. We have some while loop with a lot of initialization. You also need to do a global enable interrupt with the sci command, right? The sci macro. Now you have this while loop, and in this while loop, whenever the time 1 is equal to 0, which is this particular guy, so 1 millisecond has passed, I'm going to execute task 1. I'll reset time 1 back to t1 so that I can again start ticking down that counter with every single time that this particular interrupt service routine is called. So when 1 millisecond has passed again, I will again call this instruction. Now, the task over here, the idea is that I'm going to print on my console the period that I'm measuring. I'm going to do this in 2 ways. The first one is this particular period. I want to print this period that I've seen through the interrupt capture register. But there's also a direct way. I can also have a look at this particular AC0's position in the ACS auth register, right? So let's have a look again what that register did. That's this particular guy. And when we read this again, this is a real-time nanosecond by nanosecond binary representation of whether you see a high or a low on the IC0 output. So, what we can do therefore is to have a look what it is. Is it a high or a low? And here we say, well, if it is a high, so it's not equal to 0, and the last time that we